Two talks, we are going to move back to the world where ZK means zero knowledge and not snarks. So first, Brent will tell us about lyrics from LWE without correlation intractability.
You should call it ZK.
Yeah, I'll work on that. Okay, so yeah, thanks for having me here. I'll be talking about a new approach for non-interactive zero knowledge from learning with errors. And just as a brief overview, in a non-interactive zero knowledge proofs, or NIZKs, what we have is a prover that wants to convince the verifier of the validity of a statement or that it's in the language. And they both are given a CRS just, generated from some trusted setup process. And so the prover runs the prove algorithm, generates proof pi using its witness, sends it over in just one shot to the verifier, and then the verifier runs the verify algorithm to tell whether to accept or not. Intuitively, we're going to want to have two properties from this. First of all, we want soundness, which means if something is not in the language, then we shouldn't accept it, right? And then the second one is called zero knowledge. Never mind, or zero knowledge, where the verifier, Ron, I took care of it for you. Okay, so anyway, so the verifier learns no information about the witness W. Okay, so I think one of the most seminal works in this whole line of literature was due to Feige, Lapidotte, and Shamir, where they showed how to build NIZKs from this idealized model called the hidden bits model, a hidden bits approach. There's two parts to this. The first one, they show how to build NIZKs from some idealized model called hidden bits, where we think of as a random string being chosen and put in the sky somewhere. And the prover can choose to reveal certain bits to the verifier, but can't change them at all. And the remaining bits should be hidden to the verifier. Okay? The second part is that we're going to build some abstraction we think of as the hidden bits generator, which works as follows. First of all, there should be short or small commitments to an arbitrary number of bits. The commitment, let's say, should be statistically binding for all outputs. And then the unopened bits should be computationally hidden. Okay? And what FLS showed is essentially if you combine these two together, you get a NIZK system. Right? And this is established. So for me, I find it really fascinating to look at the history of NIZKs from number theory. As sort of a warning, here I'm just considering things in the standard model without any knowledge type assumptions, so that's all I have up here. And we see in the early 90s, we had NIZKs from factoring type assumptions. And it wasn't until, let's say, about 13 years later where the next number theoretic candidate jumped into play, which was from bilinear maps due to Canetti-Halevi-Katz. And a couple years later, there's the Groth, Ostrovsky, and Zahai thing that did it in a quite different manner, more of like a direct gate-by-gate approach is the way I think of it. Now, also in this era, Regev came up with what I'll call a number theoretic assumption of the learning with errors assumption. And what happened after that was there was a huge explosion of activity in this area, right? We had fully orthomorphic encryption, identity-based encryption, attribute-based encryption for circuits, many things we couldn't even get with bilinear maps. But strangely, even though NIZKs were older in some sense than a lot of these, NIZKs didn't come along at all until 2019. And then what I at least personally found even maybe a little more weird is it didn't use the hidden bits, didn't have a direct gate-by-gate approach. It used correlation and intractability, which I thought was strongly stuck in the random oracle model. And that to me was kind of a mystery of sorts. So what I want to ask when I looked on this work is, okay, fine, it's great that a solution came out, but why didn't the hidden bits model work? Was there something wrong with it? And what I think people might first ask is, why ask why? You know, why do we care if there's a solution out there? My first answer is that, well, I like to understand it better. Like, is there some fundamental tension between hidden bits and NIZKs, or did people just not have the right idea in order to solve it, right? Also, you kind of hope if you come up with techniques to solve something, overcome a barrier, maybe it solves something else for you. And then also, it makes intuitive. I won't claim that this is a practically efficient scheme. I'd probably get beat up over here. But it makes more black box use of underlying cryptography than, let's say, the correlation intractability stuff, right? So the result I'm going to talk about is a new hidden bits realization of NIZKs from learning with error. And that's what I'm going to go into today. OK, so let's take a little bit of a deeper look at hidden bits generators, the definition. We'll have three algorithms. The first algorithm is going to be a setup algorithm. Takes as input the security parameter and the number of output bits we want. Second algorithm is to actually generate these bits, and it should output a hopefully short commitment, bits R1 through RK, and their respective openings, right? Pi1 through Pi k. And then there's also a verify algorithm, which I'm going to say is able to verify at any particular index, verify an opening at any index and says whether it accepts it or not. We're going to want to have 3 important properties. The first one is succinctness, where the length of the commitment should be short. Ideally just polynomial and lambda, although things like polynomial lambda and logarithmic in k could also probably be okay. We want it to be binding, which is with high probability, let's say statistically binding, with high probability over the choice of the CRS. There should not be any commitment, which I can open to both a 0 and 1 at the same place. And then finally, the hiding property that a computationally bounded attacker should not be able to distinguish, let's say, the ith bit from a random bit, even if I open up everything else for you. Okay? And so if we can get this, we can get hidden bits generators. Question?
Beta is B.
Oh, no, this is like accept to reject. Beta is the bit I'm trying to open to.
So it is a bit, and that B is the answer.
And the B is just,
Yeah.
just answer. Yeah, output it. Yeah.
They're both bits, different bits.
Yeah. Okay, good. So one way of approaching this problem is to do what we call a dual mode setup. A lot of other works have something like this, where the setup can be run in one of 2 modes and produce either a binding CRS or a hiding CRS, right? And the binding CRS means it's going to be statistically bound. That is, even if let's say, if the setup is run in binding mode, the CRS that I produce, even if I'm computationally unbounded, I shouldn't be able to break it, right? And then the, in some sense, opposite thing happens for the hiding mode. I'm going to generate a CRS that even if you're computationally unbounded, you shouldn't be able to figure out what this bit is in the game I told you about. Okay? Now, we can't have both of them simultaneously, so you need to have some type of computational bridge between them, which is, says that if this computational problem is hard, you cannot distinguish a CRS in binding mode from a CRS in hiding mode. And this is the place, and indeed the only place, where we're going to use the learning with errors assumption. Just as a quick review, learning with errors roughly says that if I choose random matrix A, choose a secret S, which I won't give out, multiply it by and add noise, this should be indistinguishable if I choose a random matrix A and then let's say a vector U, a random vector U of the right dimensions. All right? Okay, so to understand this a little bit better, I first like to kind of think about the design principles behind it, yeah, and maybe give a little intuition of where things come from. So here I'm going to have something that's I call large, medium, and small. The large thing is going to be the seed for when we generate do the gem bits algorithm. The median thing is going to be the bits and all, maybe instead of proofs I should say openings, right, of all of them. And I think of this as the accumulation of all the openings together. So the seed, even if I open everything up for you and wrote down all those strings, the seed would still be much bigger than that, hopefully. Okay? And then the small thing is going to be, let's say, the commitment. Okay? And what we'll get is the succinctness will come from the fact that I bought a reasonable size one, but okay. Anyway, so the succinctness, never mind. The succinctness is comes from the fact that the commitment is small. Binding will come from the fact that when we have a structured CRS, it will lead naturally to binding. We'll see about that in a second when we get to the construction. And then for hiding, we'll have the fact that the combination of there being a random CRS component or a component of it being random and the big seed will lead to binding, or sorry, hiding in the hiding mode. Okay? Okay, so let's just dive right into the construction, yeah? And first I'm going to show it to you in binding mode, and then a little change the construction, that's the hiding mode, and then we'll see how to go between them and so on and so forth. Okay, in binding mode, we're going to run the setup algorithm. We'll have 4 steps. First, we're going to choose a prime Q, which should be, let's say, roughly size 2 to the lambda. All right. Next, we're going to set up some lattice type parameters. I'm going to be a little vague on that. Think of our smallest one as being, we're going to have an n by m matrices. So n will roughly be corresponding to our security parameter, maybe made a little bit bigger than that. M will be 2 times log of q times n, which some people familiar with this research are used to seeing that type of thing. And then my big parameter is going to be capital L, which would be m, which I had before, multiplied by number of bits, multiplied by security parameter. All right? And you can kind of see that the seed length will roughly correspond to L or L bits. And the commitment length will be N or N elements of ZQ. The next thing I'm going to do is choose a very wide matrix. So its height is going to be pretty small like N. And its width is going to be big like L. And U is going to be chosen uniformly at random. All right? And then finally what I'm going to do, or maybe second to finally, I'll choose random matrices A and WI such that AI times WI is equal to U. All right? Now, the dimensions I get of W are going to be long. What I mean by this is that the entries will be short. Yeah? So we're going to have short entries here. And OK, yeah, we can use this. We can build this from prior techniques. And then the last thing is, this is where my samples come out. This has to do with, this is the only difference for the binding mode. For each I, I'm going to choose a random vector Si of length n, some noise, and then let this vector Vi of length m be Si times Ai, and then add noise. All right? Now my common reference string is now the prime, U, all the Ais, Wi's, and Vi's. I hide these, but then everything else is given out as part of the CRS. Any questions or clear left? Mm-hmm.
The commitment here?
Sorry?
What's the commitment here?
Yeah, this is just the common reference string setup.
Oh.
We're going to do the gem bits algorithm on the next slide. Yeah. OK, and then kind of my little building here means that it's structured when we have the samples like that.
Brent, sorry, I just misunderstood.
You went last slide?
The U is defined twice. What's going on?
Oh,
You said that U is equal to A times.
use defined once in step number 2, and then I'm going to sample AI and WI such that.
Colon is such that. Okay.
Yeah. That's good. OK. Yeah. OK. Great. So now we need to do the gen the gem bits algorithm. Maybe that's what you're asking about. OK. So the first thing here is I'm going to choose my really long seed, and I'm going to choose the entries from it. Sort of a medium size, going to be between negative square root of q and square root of q. We'll kind of see why I did that later on. Next, I'm going to define my commitment as u times the seed t. So initially, the right dimension of u is really long, of length L. T was of length L. So I take this, and it compresses it a whole lot. Right? I start with a big seed, and now I get a vector of length n. Right? OK, so my commitment's small. And then in step 3, I need to come up with all my openings. And for this, I think maybe one, depending on how you look at it, one good or bad thing from this talk is we're not going to do GSW, BBG plus evaluation. I'm just multiplying stuff together here. My opening, pi I, would be WI times T. That's it. And the bit will just be multiplying the vector VI or inner product times pi I, and then doing a rounding operation. So this is hopefully all well defined. OK. And then finally, for verification, there's going to be 2 important steps. The first one is, suppose I'm trying to verify a bit at a certain index I. The first thing I do when I get my proof, I just multiply AI times pi and make sure it's equal to commitment. If not, you got to reject. And then you can just, in some sense, compute the bit. Once you have that, once you have a good pi I, you can just compute it yourself. In the same way as it's done up there, and check that it's equal to beta. And then finally, you just want to make sure that the entries of pi I are not too big. Okay, and if they're too big, you also reject. For correctness, let's see. There's 2 things to check for correctness. First of all, for step number 2, if I indeed did choose my my seed elements to be between 2 to the point around 2 to the 0.5, even if I multiply them by the WI whose entries are short, they should not, let's say, get above 2 to the lambda to the 0.6. Numbers here are a little arbitrary, you can probably see. OK, so they shouldn't, so if I did things correctly, step 2 should indeed be OK. Step 1 is a little bit more of a tricky one. So suppose I computed pi correctly, then AI times pi I should be equal to, what I can do is I can, let's say, use the fact that pi I was computed in this way and make this substitution. This is equal to AI times WI times T. And then remember from the previous slide, AI times WI was set so that's equal to U. And U times T is my commitment there.
Brendan, like step 1 of Gen, it should be lambda 2.5 or 0.5 lambda. Is that?
Sorry. Yeah.
Probably lambda 2.5.
Yeah,
Right?
you're right. Sorry about that. Yeah, okay. Thanks. Okay, good. That's okay now? Then?
So is WI part of CRS or not?
WI is part of the CRS.
So verify also know WI.
Yeah, in some sense, yeah, verifier will know the WI. Correct.
Just a generic question. You said that you're using LWE only early on to set up the reference string. So that means that you're not using any other computational assumption at this point. That's the only.
Yeah.
Everything else is statistical.
Yes,
Okay.
and in fact, I haven't even used it learning with errors yet, quite.
Yeah.
Yeah, so it's only going
I
between
was
the.
just wondering, with all those many matrices, there was some other, I don't know, SIS or something.
No, there's nothing like nothing hidden in there. Hopefully not. Yeah, I mean, obviously it'll be done in a way where hopefully learning with error will take. Okay, good. Any other questions? Okay, great. Okay, so we have correctness, and now I just want to argue why is binding mode actually binding, right? So the way I want to do this is I want to do first like what I'll call an oversimplified analysis. Right now we have VI is equal to an LWE sample. Let's imagine that I didn't have the noise in my LWE sample and see what would happen for binding it, all right? Okay, well, if the proof verifies, AI times pi is equal to the commitment, otherwise it wouldn't verify. And I derive the bit in this way once it verifies. I want to argue that this is the only, that there's only one possible output. Okay, so let's see here. Remember in my imagine mode, this is VI, right? And then if it actually verified, I can replace these two with the commitment. Is that good? And now if you just look at this, the bit that you get out of this depends on the commitment. It depends on a parameter from the common reference string and nothing else. Therefore, it's completely, once you have the commitment, you're stuck with what bit you can verify for, right? All right, well, reality is a little messier. It has this noise, let's see if I can, has this noise EI over here. So if I do the same type of analysis, what I get is the stuff that depends just on the commitment, but this EI times pi I, right? And what you might worry is if this is near the rounding boundary, there are multiple pi's that will cause verification to work. They might flip it, right, depending on which one. But the saving grace here is that since EI was small, pi I was made to be small, this thing should not be, this inner product should not be too big. And the picture we have is we kind of think of there being two rounding boundaries. Things can only really go wrong when this S times commitment gets close to the rounding boundary, right? So what we want to have is, so the way to deal with, or the easiest way to deal with it is just say, okay, verifier, if you ever try to open up something like that, you just reject. And nothing works. So you just add if it was within the rounding boundary, you reject. In practice, you can do a couple things, like you could absorb a negligible correctness error, or you could kind of shift this to the hiding. With a little bit of work, you can shift it to a hiding error. Yeah. All right. Okay, before I move on to hiding mode, any questions on why it's binding, anything like that? Okay, cool. Okay, hiding mode is going to look a whole lot like the binding mode with just one little change here. I'm going to break down my structure, and the VI is just going to be chosen uniformly at random. And that's it, right? So before we look into hiding mode, we need to see how we can get between these two. This is where the computational bridge comes into play. And really, it's only in that whether is this an LWE sample here, or is it chosen uniformly at random, right? And it seems to be almost by the definition of the LWE problem, right? Like it should be immediate. There's one little caveat here, is that remember in the parameters, we gave out this AI times WI for WI having short entries, which actually doesn't work too well with learning with errors, right? With learning with errors, it seems that you need a trapdoor in order to target this. And once you give out a trapdoor, you can no longer do learning with errors in your reduction, right? And the issue is that the reduction seems to need trapdoors for all these AI. So you can't do it. But reality is it's not too bad. If you think about it, the reduction only needs to have all but one of them. So the idea in the reduction is, let's say I'm trying to do a change on the ith one. What I'll do is get my AI, get one index AI from the LWE challenger, and pick some small random WI myself and multiply them together, call that U, right? And then everything else can kind of fit around that. Like, so you really, it's okay not to know one of them, and then you can make everything else work around it. So if we did a hybrid proof, let's see, okay, here I'm calling it J. So we can think of hybrid J as just, I don't know, the usual thing where the first J minus one of them are the V values are uniformly random. The ones above that are LWE samples. And to make the indistinguishability from J minus 1 and J, you pretty much do what I just said. Okay? So pretty easy. So not quite as easy, not maybe immediate, but not too hard either to do this. All right. Okay. Okay. So let's see why we actually hide the ith bit, and I'll try to. So the linchpin for this is that we're going to argue, if we're in hiding mode, that there will exist a short vector C with the following properties. I call it a bit flipping vector for position I. First of all, for all j not equal to I, if I multiply wj times c, the vector c, I get the 0 vector. All right? And what this means is that, 0 vector of length m. What this means is that if I had a seed, let's say, and then added c into it, you wouldn't even notice it. Like if I gave you all these openings, you wouldn't even notice that I added this seed in, right? Because I'm adding in 0. Okay. On the other hand, for the ith one, it kind of does the opposite thing. That when it does do something, and when I multiply the v times the w times the c, it gives me q over 2, which will almost always flip the answer, right? So there's going to be really two goals here. I call this one. I'm going to skip over. First of all, this comes from the last leftover hash lemma. I'm trying to keep the talk a little shorter. I'm just going to skip over showing why this vector exists, but we'll just say that the fact that it exists has to do with the seed being really long, right? The seed, just information theoretically, one of these pops out if I make it long enough, right? And then I have to show that if it exists, it hides the ith bit. So let me show you the latter of the two. It's a little easier to get through. The first one, what I'm going to do is a sequence of games. I'm going to start with gen bit 0 and change the way I'm generating my bits, argue that it's indistinguishable between each successive experiment. And then the last one, it should be obvious why the bit's hidden. OK, so the first one, we just do it like in the real scheme, choose my seed, choose my seed from, well, lambda to 0.5 as we figured out, and so on and so forth. The second one, what I'm going to do is I'm going to have a bit b, and I'm either going to add in or not add in that vector c to my seed, depending on what the bit is. Okay, that's all right. Now, the reason that these two distributions are indistinguishable is because the entries at t weren't all the way to zq, but they were pretty big. So you have a pretty basic smudging argument here. Yeah. Sorry. So yeah. So if you just whether you choose something from, let's say, 2 to the lambda to the 0.5, or that plus adding in c should be equal distribution, or very close distributions, I should say. Okay. Then the next experiment, what I'm going to do is instead of choosing like this, I'm going to just do this. And what this says is that you can essentially, if you add in, for all j not equal to I, if you add in that vector c, you won't see it in any of your proofs, just by the properties that it had. Right, so here, if I multiply, let's say, c times wj, that's equal to 0, so I can just, and also for up here, so I can just ignore it. And then down here, since this is equal to q over 2, I can kind of take it outside the with high probability, I can take it outside the rounding and just XOR the bit in. Right? Any questions? That's pretty simple. All right. So yeah. Okay, and then I think in this argument, it's pretty obvious that things get flipped. Or sorry, it's pretty obvious that there's no information about the bit that's given out. So I'm just choosing, I'm doing everything, computing everything as I would, and then with 1/2 probability, I'm flipping the bit. So there can't be anything there. Right? Okay, so that is the main scheme. I try to keep it, I think the argument about it was that it should hopefully be relatively simple. I did want to take a little bit of talk about some other work and just a little bit of a retrospective on finishing up here. So one thing, I guess, at the beginning of in research, I was trying to fall down or trying to do a bunch of bilinear map stuff. And so one question we often come across is, if we see a primitive done from bilinear maps, can we also do it from learning with errors? And at first glance, you might think, oh, yeah, of course, identity-based encryption it did, attribute-based encryption. We can do more and more and more. But there are a lot of examples out there where we've been stuck for maybe decades even, like broadcast encryption. I think that's 2 decades now, right? Even direct NIZKs, to the degree you can define that, we've been kind of stuck in. And I think it's interesting to know to have some heuristic, let's say, of where we might be stuck or not. And here's one I came up with. In bilinear maps, we have things I call target group assumptions. Like, let's say I'm given all this, and I want to distinguish E of GG that's a pairing to the ABC from just where I have this be random. So here, the thing I'm distinguishing is in the target group, right? There could also be assumption like this, where I have both things in the thing that changes is either random or structured in the source group. I call that a source group assumption. And if you kind of look at it, there's certain things where I can do in the target group assumption, which is adaptively secure IB with this sort of loss, selectively secure AB, hidden bits NIZK. And even in bilinear maps, we can do all these things, adaptively secure AB, broadcast encryption without the Q-type, direct style NIZK. But here we all need source groups. If you ask me to do this from a target group assumption, I might be as stuck on that as I am with the learning with errors. So to me, and then kind of the point is that for all the things on the left side of the slide, we do know how to do with learning with errors, and these are things we're actually pretty stuck on with learning with errors. Okay, I don't claim to have any formal theorem here or anything like that, like probably some counterexample to what I'm saying, but I don't know. I thought it's, and to me, let me also say, my bet would be if someone came up with a target group assumption for one of these problems and tried to get it to submit it to crypto, it might get rejected for being too incremental or something like that. So not that I have one in submission or anything, but just if I do, you should reconsider your position. I'm telling you ahead of time. So even though it might not seem like a lot, it actually there might be more behind there than you might be thinking of at first, right? So you could imagine it getting rejected. Oh, all right. Hopefully, we'll see. It might be your paper, Rachel. So no. All right. Well, anyway, you should consider working on it too. I guess that's the other argument. Okay, so let me just finish off by mentioning there have been a couple of follow-on works from this. One was due to myself, Ho-Tek Wee, and David Wu. There, what we did was one way of looking at this was partly given a better version of what we saw. There was transparent setup, polynomial size modulus, and a short, maybe I should say shorter CRS, linear size CRS instead of this type of quadratic thing that I have going on there in K. I would say I don't quite have this. I don't have the slides on this here. I'd say that maybe. Well, we did it in a more Ho-Tek-y way, for example. I don't know if that's if he's here or not. But maybe developing more around from the point of view of lattice tools, where for sampling your gem bits, you are given a trapdoor or able to derive a trapdoor from very short parameters, and then your CRS, so your commitment is just sort of sampling of 0, and a commitment pops out of that, right? And then by doing it in more, maybe I want to say this way, in a more in that particular way, you get to use the tools, and then your polynomial size module sort of comes for free from doing it that way. Some other people also had a similar result. They got A and B from above for learning with NIZKs, but they also used the same framework and got it from a completely or two completely different assumptions. They need, this is an and here. If they have DDH and learning parity with noise, they're able to get NIZKs. And to me, that was kind of neat to see. Okay, we can, like the ideas here do go beyond just learning with error. We can apply them elsewhere. And then finally,
Statistically sound.
yeah.
And is this a reusable NIZK? Multiple theorem?
Yeah, you can. Okay, and then the last one we in work we currently have out, currently working on, we can turn this into a 2-round witness and distinguishable proof, and sort of again a different way of doing that. Okay, well, so to conclude, the hidden bits model does indeed work with NIZK, sorry, with learning with errors, and as some retrospective, actually I should give Hotek some credit for kind of making me think about this a little bit more than I was. I think it's also different than other hidden bits solutions in the sense of if you look at the RSA solution, the commitment is just this trapdoor, right? The common reference string just gives you a bunch of images, isn't even aware of what your RSA modulus, let's say, is, and you just have to operate on them, right? Here, there's not really a trapdoor. Instead, there's more like a joint sampling of the small commitments. So even though like this isn't just like, oh, I took the RSA solution and I figured out a learning with errors way of doing it, it's quite, in some sense, different than the RSA way of doing things. Right. Okay, well, thank you very much. And I got us back on time.
So you do have two different reference strings, one for soundness, one for zero knowledge, right?
Yeah, two different types, yeah. Right.
No more questions?
Yeah.
Okay. Yeah.